Welcome to day 19. Homework is packet page 10. Make sure to do it on a separate sheet of paper. For the first few, you wanted to tell whether they converged absolutely, conditionally, or diverged. In the first one, because ratio of leading coefficients, because same degree, the terms are going to go to 2/3. That's not 0, so that diverges by the nth term test. In the next one, pull the 2 out, and then it's 1 over n to the 4th. That's p series, p greater than 1, so it converges. It's always positive, so even the absolute value version of it will be the same, so it must be absolutely convergent. Next one, we're going to compare our original series to 3 to the n over n factorial. For that series, do a ratio test, next term divided by current term. With your factorials, you got an n plus 1 left on the bottom. With your 3's, you got a 3 left on top. As n goes to infinity, that's 0, which is less than 1, so therefore it converges by the ratio test. Well, now we'll divide our comparison series and the original one. We'll end up with 3n plus 1 over 3 to the n plus 1 over 3 to the n. Divide them both by 3 to the n, that's 1 plus 1 over 3 to the n. As n goes to infinity, that is a positive finite number, meaning our series that we're looking at must do the same as our nice one. So our series we're looking at converges due to the limit comparison test. Since it was always going to be positive, that means it is absolutely convergent, because when you do the absolute value of it, it wouldn't change anything at all. In 4, a factorial is going to grow much faster than an exponential. Even though exponentials grow fast, factorials are going to eventually be multiplying by things more than 10. So therefore, that will diverge by the nth term test. In 5, this one might have been a little tricky. We're going to compare this to 4 over n squared. Now, the reason we're picking 4 is that is a numerator that is guaranteed to be bigger than 2 minus cos n, because the biggest 2 minus cos n will ever be is 3. So we've got something that's always greater than what we have. Our comparison, the p series converges because p is greater than 1. So because 4 over n squared is always bigger, everything smaller than it will converge. So we can say our series converges by the direct comparison test. Since our series is always going to be positive, even when you subtract the smallest thing, subtract a 1, it's still going to be positive, so therefore it converges absolutely. In 6, we'll do the ratio test. We have an extra negative 3 on top, but we're doing absolute value. That's why it's just 3. Then your factorial and squareds part. As n gets huge, that limit will be the same as just if you looked at the factorials, because the factorials are going to control the value. So what's written in the thicker black pen there is the same limit as the original one we have. Well, that'll give you 1 extra n plus 1 on the bottom. So as n goes to infinity, that's going to head to 0, which is less than 1. So our original is converging by the ratio test. When you do the absolute value of that, essentially you're going to end up with the same thing, because our ratio test did the absolute value of it anyway. So therefore, you will get it to converge absolutely. In 7, first do the sum of the first 15 terms. You can do that right on your calculator. We were alternating, so our error is just the next one, the 16th one. So that's 16 over 4097. In 8, how many terms are needed to be within 0.05? So we'll do alternating series error bound. Don't worry about the negative. We'll put in 1 over x in our calculator, and we need it to be less than or equal to 0.05. The first term that you see to do that is your error term, remember? And then the term before that is the one that we would need to go to. So 20 is the first one. So therefore, 19 terms is what we'd have. In 9, do 1 over x cubed or 1 over n cubed. We want to be less than 0.0005. Remember, the term that you find is the error term. So the one before that is the term we want to go out to. So you would get the 12th term. Now in both these, just be careful to make sure they have 1 on the bottom. Because if it says how many terms, like let's say we were doing number 9. and we found that error term was n is 13. So the term we want to go to is n is 12. Well, if it had had an n equals 0 on the bottom, well, then that would be an extra term that we'd have to do. So just be on the lookout for that. That can be one thing to make it just slightly trickier. In 10, do your partial sum for the first 10 terms. Put 10 on top, do it in the calculator, see what you get. Alternating series error bound, use the next term, you get 1 over radical 11. And to write that with bounds of our actual amount, take our 0.451 minus the 1 over radical 11. That'll form a lower bound. Add it, it'll form an upper bound. And often you see it left just like that and not actually combine them. Take your Maclaurin for cos out to the 4th degree, sub in -1, you get 13/24. And then do your next term and sub in -1, absolute value. That'll give you the maximum error, the 1 over 720. All right, we want to do sine of 5, and we wanted to know how far do we have to go to stay less than 10 to the -6. Well, 10 to the -6 is the same as 0.50 and 1. Or since your calculator is going to switch it to scientific notation, we're looking for the first thing that shows up as a 10 to the -7. So we're going to put in 5 to the n, because all the x's are being replaced with 5s, over n factorial. And we'll put those in with x's in a graphs page and do a control T. Now, when we're looking in our table, keep in mind the way we have this is 5 to the n over n factorial, signs only odd powers. So in your table, you shouldn't even be looking at the even ends. Only look at the odds. So look at 17, not small enough. 19, not small enough. 21, not small enough. 23 is the first one that is smaller than 10 to the -6. So that's our error term. So the odd term before that is the one we want to go to. So we have to go out to the 21st degree. Then we did the same question, but with 0.5. Do a similar idea. We're only looking at the odds. So 5 was not small enough. 7 was not small enough. 9 was, so that's our error. So therefore, we want to go to the previous odd one, so 7th degree. If we had been doing a cos, which has only even powers, we would only want to look at the even ends. Sub in -2 out to your 5th degree term for e to the x, we get 1/15. Your alternating series error bound, go to your 6th degree one, to the absolute value, you get 4/45. And then for Lagrange, to pick out our m value, our center's at 0 and we had -2. So from -2 to 0, we need to think of our next derivative, our 6th derivative. Well, 6th derivative of e to the x is still just e to the x. And if you think of the graph of e to the x from -2 to 0, 0 is going to be the highest value, and that's something nice. It's 1. So just put in 1 for your m. You've got -2 minus your center of 0, absolute value of that raised to the 6th, and then over that next term factorial, 6 factorial, happens to give us the same thing here, 4/45. Usually, alternating series error bound is easier here. Then in this case, they happen to give us the same. So neither of them was tighter. And if you used +2, we could not have used alternating series error bound because it would not have created an alternating series when we put in 2. So we're going to be in day 19 notes. So I think it was on day 12, we looked at our Taylor polynomials for the sine graph. And we saw as we added terms, it was a better and better fit as sine went on. So we knew, if we go down to the bottom, sine was that summation from 0 to some k. And as k increased, it became a better approximation. All those approximations had some amount of error, which we could approximate what that error was. But could we eliminate that error if we let it go to infinity? This infinite series, which is called a Taylor series as opposed to a Taylor polynomial, would match the sine function exactly. So does the Taylor series always converge to the function it was constructed, and does it do so infinitely? For the sine graph, it does. If you go to infinity, that's going to keep wrapping around the sine graph and match it exactly. But that doesn't necessarily always occur. So here's 1 over 1 minus x. Notice as our number of terms as we keep going out, it does seem to match it better and better and better, but there seems to be a window where which it'll only match it. And for us, it looks like -1 to 1 is approximately that window. Outside of that, it doesn't appear to be getting any better. So it seems there's some type of bound on this one where we can actually approach the function. Here's another one, square root of x. As we add values, I don't have the polynomial written out there, but just have it labeled. So we have the second degree, fourth degree, fifth degree polynomial, which it does appear to match it better. But again, there seems to be some bound for how far it'll match the function. It doesn't seem to be going on infinitely like the sine. This one around 0 to 8. So the set of x values for which a Taylor series, so Taylor series again means it's going to infinity, will converge on our function we're trying to represent is called its interval of convergence. The center of the series is always right in the middle of that interval. So like in the square root example, 4 would be our center there. And the distance from the center to either of the endpoints of the interval is called the radius of convergence. So you might be asking, well, that's all great, but how do you actually figure out what that interval is? So if we go to the next page, let's say we've got some power series, and it's in this form. Well, this is a new term, a power series. It's definitely a series that's going from something to infinity. But what are some different things the power series could look like? And we have those down on the bottom. The first 3 are examples of power series. The second 3 are not power series. To be a power series, you have to have some consistent center and then raised to successive powers, either going by ones or in some pattern. So the first 2 on top, the powers are going up by 1 each time, the third one going up by 2s. It needs to be in the parentheses x plus something or x minus something, and that represents the center of your power series. So in the top one, the center's 3, because it's always x minus whatever your center is. In the second 2, it's 0. That center cannot switch. It's got to be consistent throughout. And then there's some type of pattern with coefficients out front. And that pattern of coefficients could change depending on what you have. Now, it can't be factorials, can't be things in the bottom, can't be trig functions. So those are all not power series. So again, our interval of convergence, it's a span of values where the power series will converge to the function. And there's 3 things that could occur in our interval of convergence. It could be just a single point at the center, because your series will always match the original function at the center. It could be some set interval. The interval could either include the endpoints, not include the endpoints, or it could be a combo of not including and including, or including and not including. The radius in that number 2 there, notice, is from the center to the endpoint. And then you could have a situation where the series converges for all real numbers. So in other words, in that case, we would say that our interval is just from -infinity to infinity, and our radius would be infinity. If it's the number 1 case where it's just a single point, we would say our interval is x equals whatever our center is, and we would say that our radius is equal to 0. So 1 and 3 are kind of the special cases. So let's work on actually finding an interval of convergence. We will always use the ratio test to find that interval of convergence. Remember, ratio test, we do limit as n approaches infinity of next term divided by current term. So we're going to do limit n approaches infinity, absolute value. Our next term would be 4 times x minus 2 to the n plus 1 divided by our current term of 4 times x minus 2 to the n. Well, this is going to be limit as n approaches infinity. If we neaten up, the 4's divide out. All but one x minus 2 will divide out. As n goes to infinity, that doesn't involve any n's there, so this is just absolute value of x minus 2. Now let's think about what had to be true to converge with the ratio test. We needed our limit to be less than 1. So we're going to throw a less than 1 now on the end here, because we need to know when is that absolute value of x minus 2 going to be less than 1. That will be when it's going to converge. Well, when you have an absolute value, that could be the positive or negative version of it. So to rewrite an absolute value inequality without the absolute value, we would rewrite this as negative 1 is less than x minus 2 is less than 1. Because basically it's saying that x minus 2 needs to be a negative or positive decimal or 0. That's essentially what that's saying. Well, now we just solved this. We got to add 2 to all the spots. So we got 1 is less than x is less than 3. So that's what we have so far for our interval of convergence. We're not done yet, because we're going to have to check our endpoints to see if they're included or not. But let's first talk about the meaning of this. So, what's meant by the fact that we know between 1 and 3 converges, if you picked a value like 2.5, sub it in for x, you would get 2.5 minus 2, which is a half, and now you have 4 times a half to the n. Well, notice that's geometric with r value less than 1, so that converges. If we did it outside of the interval, like x equals 5, 5 minus 2 is 3, so we'll get 4 times 3 to the n. That's geometric with an r greater than 1, so that diverges. So that's the meaning of it. The x values in our interval will cause the series to converge when you sub them in. Not always going to be geometric. We'll see instances where it's not, but in this particular case, it is. So, going down to the bottom, let's check those endpoints. So we're going to check x equals 1. Where this negative 1 is coming from is in the parenthesis we did 1 minus 2. So you sub the 1 in for x. Well, this is 4 times negative 1 to the n. We could say that this diverges since geometric, absolute value of r is greater than or equal to 1. You also could have said that it diverged because of the nth term test as well. So therefore that one diverges. And then we can do the same idea. The x equals 3 is coming from subbing in 3 in for x up in our series up above. 3 minus 2 gives you 1. So we could also say this diverges since geometric, absolute value of r is greater than or equal to 1, or you could say diverges by the nth term test. So because it diverges, our final interval is going to be 1 less than x less than 3, and our radius of convergence, our center was 2, so from 2 to 3 or 2 to 1, that would be a radius of 1. If we had gotten x equals 1 to converge, but then x equals 3 didn't, we would have had something like this. If the 3 had also converged, then that would have an equal to. So when you check your endpoints, you're just deciding if you should include those values or not. And again, you're just subbing those into the original series and then doing any of our tests that we've done so far to see if they converge or diverge at those endpoints. So if we look at that series we've been working with from a graph, you can see it appears that around from 1 to 3, that's where it is matching nicely. and then outside of there it does not match as well. So let's try another one. We want to find the interval of convergence, so we're going to do the ratio test. So we'll do absolute value of next term divided by current term. Well, with our factorials, from n all the way down is going to wipe out. So we're going to have an n plus 1 left in the numerator. For our x's, all but one x is going to wipe out. So as n goes to infinity, this is going to blow up. We need it to stay less than 0. Well, this is never less than 0. So, therefore, this is going to converge only at the center, because the center will always match exactly. So our interval of convergence is just the center. In this case, our center was 0, because it was like x minus 0 raised to the n. So x equals 0 is our center, and our radius would just be 0. We'll look at one last one for this video. We're going to do the interval of convergence, so we'll do our ratio test. Now, because we're doing the absolute value, you can ignore that negative 1. We'll do x to the 2 n plus 1 over, this is going to be n plus 2 factorial. When we divide by the current term, we're really multiplying by its reciprocal. So that'll be n plus 1 factorial over x to the 2n. So this is really x to the 2n plus 2. So that means there are 2 extra x's on top, so x squared. With our factorials, everything will divide out except for the n plus 2. N is only on the bottom, so when n goes to infinity, denominator is going to get huge, this will approach 0. And this, therefore, will be always less than 1. Most times you'll have something that has an x in it, so it'll be like that first case we did where you've got to write the two-part inequality and check the endpoints. Last one and this one are the special cases. We're always less than 0, so this means it converges everywhere. So our interval is just negative infinity to infinity, and our radius would also be infinity. That's it for this one. Have a great rest of your day.